Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Saleh Ali Al-Dini, and today I will talk about the first chapter of mechanical vibration, which is Fundamentals of Vibrations. And this presentation will be under the supervision of Dr. Futayan Ahmaduddin. All the information of this presentation were taken by the book of Mechanical Vibration by Singer's US Raw. Here are the titles that the first chapter focuses in, and we will go through them in this presentation, inshallah. After finishing the first chapter, we will be able to describe the history of vibration, indicate the importance of study of vibration, give various classifications of vibration, state the steps involved in vibration analysis, compute the values of spring constants, masses, and damping constants, define harmonic motion and different possible representation of harmonic motion, add and subtract harmonic motion, conduct Fourier series expansion of given periodic function, determine Fourier coefficient numerically using MATLAB program. The first title of the chapter is preliminary remarks, which can be considered as introduction of the chapter. The chapter begins with a brief history of vibration and continues with an examination of its all importance. We learn that all mechanical and structural systems can be modeled as mass, spring, damper systems. The chapter describes the modeling of mass, spring, and damping elements, their characteristic and combination of several spring, masses, or damping elements. And we will learn the concept of harmonic analysis, which can be used for the analysis of general periodic motion. The second title in this chapter is Brief History of the Study of Vibration. First of all, we'll talk about origins of the study of vibration. The study of vibration has a long and rich history. Early observation of vibrating systems such as musical instrument and human voice led to the development of basic concept of acoustic and music theory. The Greek philosopher and mathematician Pythagoras discovered the mathematical relationship between musical notes and the length of the vibrating strings. Second of all, we will learn how the study of vibration developed from Galileo Galilei to Rayleigh. First of all, Galileo Galilei, investigating the motion of pendulums and formulated the laws of simple harmonic motion. And then Sir Isaac Newton developed the laws of motion and the theory of gravitation, which provided a fundamental framework for understanding the dynamics of vibrating system. After that, Leonhard Euler made significant contribution to the mathematical theory of vibrations, including the development of the wave equation. Then Joseph Lagrange formulated the Lagrangian mechanics, a powerful tool for analyzing the motion of complex systems. And then Lord Rayleigh published the seminal work, The Theory of Sound, which laid the foundation for modern acoustics and vibration theory. The third subtitle will be Recent Contribution, and we will divide this subtitle into 4 parts. The first part is early contributions. First of all, from innovations, he investigated the torsional vibration in steamship propeller shafts and proposed the dynamic vibration absorber to eliminate vibration in primary systems. And then there are some scientists, we can consider them as pioneers in vibration theory. For example, Oral Stadella studied vibration in beams, plates, and membranes, developing method applicable to turbine blades. Then CGP de Laval addressed vibration in unbalanced rotating disks and demonstrated particle solution using high-speed rotors. And there are Stephen Tomaszenko, he introduced thick beam theory incorporating rotary inertia and shear deformation. And after that, R.D. Mendlin developed a similar theory for thick plates. The second part will be nonlinear vibration. First of all, the mathematical foundation. Poincaré developed the perturbation method in 1892, and Lyapunov introduced modern stability theory, applicable to all dynamic systems. Secondly, further developments. Duffing and van der Poel provided specific solutions highlighting the importance of nonlinear vibrations in engineering. And then Navy survived modern perturbation theory for nonlinear systems. The third part is random vibration. Concepts of random vibration gain importance with phenomena like earthquake and jet engine noise. Advances include the correlation function and spectral density. And of course, Len and Rice's work to apply random vibration theory to engineering problems. The last part of recent contribution will be computational advancements. Firstly, digital computers and numerical methods enabled detailed analysis of systems with thousands of degrees of freedom since the 1950s. Secondly, the finite element method. It's originally conceptualized centuries ago. It was formalized for engineering application by Turner, Clough, Martin, and Toop, revolutionizing vibration analysis of complex systems. The third title is the importance of the study of vibration. Vibration is important in several ways. as we can see, first of all, vibration in everyday life, because it's fundamental to human functions such as hearing, seeing, breathing, walking, and speaking. Secondly, it's important and critical in the design of machine, foundation, engines, turbines, and control system. Third of all, vibration can lead material fatigue, wear of components like bearings and gears, and failures in structure systems due to cyclic stress. Vibration transmitted to human cause discomfort. And the key goal is to reduce the vibration by designing machine with minimal imbalance and supporting structure that mitigate harmful effects. Learn how to convert vibration to sound by human ear. First of all, vibration generates pressure waves in the air, which the ear recognizes as sound if their frequency fall within the audible range, which is from 20 to 15,000 hertz. The human ears consist of three parts. The first part is the outer ear, direct sound wave to the eardrum. The second part is the middle ear, transfer vibration from the eardrum through the hammer, anvil, and oval window. The third part is inner ear, convert vibration into electrical impulses via hair cells in the basilar membranes. These impulses are interpreted by the brain as sound or noise, so the brain can recognize it. Here we can see the figure and we can see the three parts of the ear. And we can know how the ear will convert the vibration into sounds to recognize it. The fourth part of this chapter will be the basic concept of vibration. First of all, we should understand what's the vibration, and we can define the vibration as an emotion that repeats itself after an interval of time. And the swinging of pendulum and the motion of plucked string are typical examples of the vibration. Secondly, the elementary part of vibrating systems, or we can see the components of vibrating system. First of all, the spring or elasticity. It stores potential energy. Then we have the mass or inertia. It stores the kinetic energy. And thirdly, we have the damper, which gradually dissipates energy. Here we have an example, which is the simple pendulum. At the extreme position, the pendulum has maximum potential energy and zero kinetic energy as it swings. Potential energy converts to kinetic energy and vice versa. At the mean position, kinetic energy is maximum and potential energy is minimum. And for the damping, for example here, air resistance gradually reduced the oscillation amplitude until the pendulum stops. The third part will talk about the numbers of degree of freedom. The degree of freedom of system is the minimum number of independent coordinates required to describe its motion completely. For example, as we see before, the simple pendulum, we can consider it as a single degree of freedom system, as its motion can be described using one independent coordinate, such as the angular displacement. Here in this figure, we have several examples about the single degree of freedom. For example, slider and crank, and spring mass system, and torsional system. And for multi-degree of freedom system, multiple independent coordinates are needed. For example, a 2-mass 2-spring system requires 2 coordinates to describe its motion, while 3-degree of freedom system needs 3 concentrates among the coordinates, such as x squared plus y squared equal L squared. For a pendulum, reduce the number of independent variables. And here in these figures, we can see 2-degree of freedom systems and 3-degree of freedom systems. But here we can see infinite number of degree of freedom system, which can be an example of cantilever beam. Now we can know that system can have either a finite or infinite number of degree of freedoms. Discrete system like simple mechanical models have finite degrees of freedom, while the continuous systems such as beams or rods have infinite degrees of freedom due to their elastic deformation. Also, the continuous systems are often approximated as discrete systems for simple analysis, using lumped masses, spring, and dampers. And when increasing the number of these elements, that improve the accuracy while maintaining practically the studying of complex systems. Classification of vibration. Vibration can be classified in several ways. The first way, free and forced vibration. The free vibration occurs when a system vibrates in its own after an initial disturbance without external forces. For example, the simple pendulum. Secondly, the forced vibration happens when a system is subjected to an external, often repetitive force, such as in diesel engines. The second way to classify vibration is undamped and damped vibration. Undamped vibration occurs when no energy is lost during oscillation. And the damped vibration involves energy loss due to friction or resistance. And it's often negligible in many systems, but it's become crucial in analyzing vibration near resonance, where even small damping can significantly affect the system behavior. The third way is linear and nonlinear vibration. The linear vibration occurs when the spring, mass, and damper behave linearly, and that leading to linear differential equation. Nonlinear vibration arises when any component behaves nonlinearly, resulting in nonlinear differential equation. The fourth way of classifying the vibration is deterministic and random vibration. The deterministic vibration occurs when the excitation acting on a system is predictable and known at any time. And secondly, the random vibration arises when the excitation is unpredictable or random, such as the wind velocity or ground motion during earthquake. And as we can see in the figure, the deterministic and random vibration. And for the vibration analysis procedures, there are four steps. The first step is the mathematical modeling, which means develop a simplified representation of the system focusing on its key features. Secondly, derivation of governing equation using principles like Newton's second law or energy conservation to establish equation of motion. Third step is solution of governing equation by solving the equations to determine the system's response. For example, displacement, velocity, acceleration. The fourth step is interpretation of results, and that means analyze the solution to understand the system's behavior and derive design insights. And here, as we can see, this is a model of vibration analysis procedure, which is a modeling of forging hammer. And now we will talk about the spring element. As we know, the spring is a key component in mechanical systems, often analyzed as massless and undamped. They exhibit a force displacement relationship with linear springs, obeying the Hooke's law, which is the force is equal to the spring constant multiplied by displacement. First of all, we'll talk about nonlinear springs. Many real-world springs deviate from linearity due to the material properties, geometric changes, or contact interaction. This nonlinearity complicates analysis and can lead to complex behaviors like jump phenomena and subharmonic resonances. Secondly, we'll talk how to linearization for small displacement. So, nonlinear spring can be approximated as linear by determining an equivalent linear spring constant, which is K, at the operating point. This allows for simpler linear analysis techniques to be applied, and that will help us solve many problems. And there are a lot of examples in this title. Thirdly, we'll talk about the spring constant of elastic elements. And this subtitle explores how to determine the spring constant for various elastic elements like bars, beams, and torsion springs, considering factors like geometry and material properties. And then we'll talk about the combination of spring methods, which are presented for calculating the equivalent spring constant of systems with multiple springs connected in series, parallel, or more complex arrangement. And as we can see from textbook, an example in this subtitle to calculating the equivalent spring constant. And the last subtitle will be the spring constant associated with gravity. The effect of gravity on the spring constant is considered, particularly in vertical systems where gravity influences the equilibrium position. So in vertical system, the gravity is important and it will play an important role in the spring constant. Here we can see in these figures the combination of spring. Here in the first figure, spring in parallel and spring in series in the second one. And there are a lot of examples in the textbook that solve the problems relating to the springs. This part we will talk about mass or inertia elements. In this section, the concept of mass is a fundamental property of matter that resists changes in its states of motion and that knows as inertia. First of all, mass is a crucial component in any vibrating system. It stores kinetic energy during motion and influences the system's natural frequency and responds to external forces. Then we will talk about the equivalent mass. This subtitle likely discusses how to determine the equivalent mass of a system with multiple masses connected in various configurations, series or parallel, like we saw for the springs. Lastly, from this part, we'll talk about the center of mass, which is the concept of the center of mass is likely which is the point where the entire mass of the system can be considered to be concentrated for certain types of motion. As we can see here, the combination of mass equivalent. As we see in the first figure, the translation mass is connected by a rigid bar, and in the second figure, translation and rotation masses in a rack and pinion arrangement, which are the two cases of combination of masses equivalent. And now we'll talk about the damping element. The concept of damping is a dissipative force that opposes motion and gradually reduces the amplitude of vibration. In other means, we can say it converts the vibration energy into sound or heat. Damping is important because it reduces the amplitude of vibration, preventing excessive oscillation, and improves the stability and performance of mechanical systems. Also, damping isolates systems from external vibrations. And there are types of damping. First type is viscous damping, which is the most common type where the damping force is proportional to the velocity of the motion. The second type is column damping, which damping force is constant in magnitude but opposite in direction to the velocity. The third type is hysteresis damping, which means energy is dissipated within the material itself due to the internal friction. The chapter focuses on the construction of viscous dampers because it's the most common type, and there are a lot of examples of viscous damping. For example, the dashpots, which device filled with viscous fluid that resists motion. Also, the shock absorbers, used in vehicles to absorb the energy of road bumps, like what we see in movies and highways. The next subtitle is linearization of nonlinear dampers. In the real world, damping mechanism often exhibit linear behavior, where the damping force is not strictly proportional to the velocity. So linearization means to have approximate linear damping with an equivalent linear damping coefficient for a small displacement, similar to the linearization technique used for linear springs, as we explained before. And for the equivalent damping, we will know how to determine the equivalent damping coefficient for system with multiple dampers connected in series or parallel, like we see in the springs and masses. And now we will talk about the harmonic motion. In this section, the harmonic motion is characterized by sinusoidal or cosinusoidal vibration. And there are important concepts. For example, period, it's the time for one complete cycle. The frequency is the number of cycles per unit of time. The amplitude is the maximum displacement from equilibrium. And phase angle determines the starting point of each oscillation. Secondly, we'll talk about vectorial representation of harmonic motion, or can we define it as phasors. The phasors is a harmonic motion can be visualized using rotating vectors, which is phasors. The phasor link represents amplitude. Rotation at constant angular velocity represents the harmonic motion. Secondly, we will talk about the complex number representation of harmonic motion. Of course, the harmonic motion can be represented by complex numbers, which by a mathematical framework using imaginary numbers. And there are a lot of examples and equations in the textbook talking about this. And third thing is complex algebra, which is essential tool to provide overview of complex number operation. For example, addition, subtraction, multiplication, division. And Euler's formula is used for complex algebra. And in this part, we will learn how to demonstrate operating in complex number, for example, adding or subtracting to harmonic motion, or differentiate and integrate harmonic function. And of course, analyzing the superposition of multiple harmonic motions. And there are definitions and terminologies we should understand. First of all is the cycle. It's the movement of vibrating body from its disorb or equilibrium position to its extreme position in one direction, then to the equilibrium position, then to its extreme position in other direction, and back to equilibrium position. It's called a cycle or vibration. Secondly, the amplitude, which is the maximum displacement of vibrating body from its equilibrium position. Third of all is period of oscillation, which is the time taken to complete one cycle of motion is known as the period of oscillation or time period. Then we have natural frequency. After an initial disturbance is left to vibrate and so on. The frequency with which it oscillates without external forces is known as natural frequency. Then we have beats. When two harmonic motions with frequencies too close to each other are added, the resulting motion exhibits a phenomenon known as beats. After that, we have octave, when the maximum value of range frequency is twice its minimum value. For example, 75 to 150 Hz, known as octave band. Lastly, we have the decibel, which is the various quantities encountered in the field of vibration and sound, such as displacement, velocity, acceleration, pressure, and power. And now we will talk about the harmonic analysis. In this section, we will deal with the analysis of more complex periodic signals that can be represented as a sum of simpler harmonic motions functions. First of all, we'll have Fourier series expansion. We will understand the concept of Fourier series, which is a powerful mathematical technique used to represent any periodic function as a sum of sine and cosine functions. And this allows for the decomposition of complex waveforms into simpler harmonic components. And we can go through the textbook and we can see the graphs and equation of Fourier series expansion. Secondly, we'll talk about the complex Fourier series, which is a complex form of Fourier series, which provide a more concise and mathematically elegant representation. It utilizes complex exponential to express the series, often simplifying the calculation and analysis. The third thing will be frequency spectrum, which is a graphical representation that shows the amplitude or power of different frequency components present in a signal. It provides a visual understanding of the signal's harmonic contents. The next thing will be time and frequency domain representation. And here we will discuss the relationship between the time and domain representation of a signal, which means how the signal will vary with time, and its frequency domain representation, the distribution of frequencies present in the signal. It highlights the importance of both representations in understanding and analyzing signals. And the next thing will be even and odd function. And here we will discuss how can simplify the calculation of even and odd function can make a good role in simplifying a calculation of Fourier series coefficient. Even and odd functions have specific symmetries that lead to simplification in the Fourier series expression. The next method will be the half-range expansion, which is focused on the Fourier series that defined only over a half interval by extending the function's definition to the entire interval using even or odd extensions. Appropriate Fourier series representation can be obtained. The last method we have will be the numerical computation. And this method will discuss the numerical for calculating Fourier series coefficient, especially for functions that don't have readily available analytical solution. It may cover techniques like the fast Fourier transform, which is an efficient algorithm for computing the Fourier series. And if we go through the book, we can see the equation of each method, and we can understand how to use them to solve any problem related to harmonic analysis. The next title will be examples using MATLAB. But the most important question, why MATLAB? And that's because MATLAB is a powerful and versatile tool for solving vibration problems due to its strong numerical computation capabilities. It excels at solving differential equations, performing matrix operations, and visualizing data, which are essential for analyzing the dynamic behavior of vibrating systems. MATLAB Control System Toolbox and Signal Processing Toolbox provides specialized functions for vibration analysis, control system design, and signal processing. That's why there are a lot of problems we're solving using MATLAB in the textbook. In this chapter, we presented the fundamental concepts of vibration along with a brief outline of the history and the importance of the study of vibration. We introduced the concept of degree of freedom, discrete and continuous systems, and the different classes of vibration. We introduced the fundamental types of vibration, namely harmonic motion, along with associated terminology. And we presented the method of harmonic analysis and Fourier series representation of periodic function, as well as numerical determination of Fourier coefficient. And there are a lot of good information. We can see them in the textbook, and we can revise the examples to very understand the concepts. Thank you for listening. And that's all for my presentation of first chapter on mechanical vibration. Assalamu alaikum wa rahmatullahi wa barakatuh.